Welcome to Lecture 15 on Perception-Based Manipulation. So far in our course, we have covered modeling from part number 2 and perception from part number 3. Then later, we introduced manipulation from part number 5. In this chapter, we're going to be integrating the modeling, the perception, and the manipulation to form a complex system. What we're interested here now is to execute goal-directed behaviors. These are going to come from our perception system. And so we're building on everything that we've been doing before, but now we can provide the goals through our cameras and then use that with our manipulation, planning and execution to help the robot reason about the world to achieve specific goals. That's very important because this now gives us the ability not to just run hard-coded solutions, but to be able to adapt to a changing behavior, to be more reactive, and to be more autonomous. This is ultimately what we all want to do. So get ready just to see how we're going to do this in this lecture, which is going to be a very exciting moment. Before we get to using perception, just want to clarify a little bit more on extrinsic camera calibration. And this section here, 15.1, we're going to just try to understand the effects of this transformation and how does it look when it's right, how does it look when it's wrong. From our previous lecture, back in, I think, Chapter 7, I introduced this slide. We said that extrinsic camera calibration is necessary to grasp objects whose goals come from vision. And we're really just very interested in computing the transformation between this camera frame over here. In this picture, we have a Kinect sensor being held by this support beam, and the robot, target frame over here. So the target frame may vary, but commonly it will be this tool frame in between the gripper or the gripper fingers. So this yellow line is what we're interested in doing. We know that the transform between the robot base frame and the contact point is green. This one we can get from the forward kinematics. We know the transform between the camera link frame and the contact point. This one we can get from vision algorithms, given that we have proper intrinsic calibration in the camera. So if we have this and we have this, we want to be able to compute then this transformation. Okay, so that's what we talk about when we do extrinsic calibration. Now, if the calibration is correct, that means that the points, say from a depth image or a depth camera, those points will exactly match with those of the surfaces in the real robot. So let's run that, and we'll see how the points align with the arm. Let's open a terminal. First thing we're going to do is run gazebo empty. The next thing we're going to do is launch the package Baxter Variations. We're going to put Baxter on a pedestal, include a Kinect, and also include a table and a toy. So when you run that, you see here the pedestal, and you see the robot, you see the table. If the toy shows on the floor, which can happen from time to time, we need to remember to run the example gazebo set state package reset block state node that will return that block to the right place. So now we have the environment ready. The next thing we want to do is run everything that we need for manipulation to take place so including our planners, our playback files, RViz, and a host of other nodes that we're going to see in a second. So we run coordinate vision manipulation.launch. This is going to get everything ready for Baxter to execute. It also has prepared configuration for RViz. The arm moves to this pre-post position. If your Baxter is not moving, maybe you'll need to manually enable it and then try running again. Sometimes that can happen. So we have a robot in this position. And finally, the last thing we want to do is run the play file node. So we take the package Baxter play file nodes, and then the node Baxter playback, and we pass this file. By the way, before we do that, as I showed right here, we'll need to raw CD to the right location, Baxter play file node. So you can see that I'm right here, raw CD Baxter play file node, like this one. And then we can run this command with Baxter playback can grasp pose.jsp. So we'll see how the Baxter arm is moving. And really here, the most interesting part, what we're really trying to look at, is how these points on the point cloud seem to perfectly align with the real physical structure of the robot. So it's very clear here on the forearm that those points seem like they're painted on the arm. Same right here with the hand. There is a perfect agreement. Okay, here with the upper shoulder as well. Okay, so this is what correct extrinsic calibration looks like. Everything agrees between what the vision system says and what you actually have in the environment, especially here with the robot. Now, to do correct eye-hand calibration, there's many challenges, including unrealistic CAD models when we use simulations. So if your CAD model is not accurate, it's going to be hard for you to evaluate whether this is working or not. Talking about simulation. With the real robot, there's other kinds of challenges. How accurate is the precision of our joint sensors? How accurately can we tell the configuration of the arm? If we have some mistakes there, our kinematics are not going to be good, and then it's going to be hard to find that agreement between the visual system and the arm. Even our kinematics, sometimes in kinematic models, people might use an approximation to simplify the mathematics for analytical derivations of inverse kinematics. So if that is not correct, you're also going to run into trouble here. The home angle calibration. A robot needs to know where 0 starts. Where is the home position? So if there's a little bit of noise in there, every other pose will be affected from that. That can be a source of error. So there's many things that we need to ensure are working properly before we can calibrate the visual system with the manipulation system. Now, if your URDF is precise, in this case, Baxter's model is very good. RViz can be used actually to adjust the transformation and close that gap between vision and reality. So we're going to look at how we might be able to do that next. So we're going to start by introducing errors in some of the transformations. we're going to corrupt the transformation within 2 of the frames of connect. Now this is just an easy way to corrupt this calibration, so this is an example where we do that. Inside the connect camera we have the connect link and the connect point cloud frame. The point cloud frame is the location of the frame for the depth camera, and the connect link is the center of the whole camera. So we're going to be changing this transformation. To do that, we're going to do a couple of things. Number one, we're going to use a different launch file for the Baxter Variations package. This launch file does not include this transformation right here. So actually, let me open the correct launch file in this side. So we use raw set, Baxter Variations, Baxter on pedestal with connect.launch. And you'll notice down here that we have 2 transformations. One from connect link to connect depth frame, another one for connect link, connect PC frame. When we use connect2.launch, these 2 transformations have been commented out. Okay? So this correct transformation is missing, in particular that there's no change in XYZ position. The incorrect transformation is now going to be included in a new launch file called connect_transform.launch. And here we include a small error, a displacement of 10 centimeters in the X, Y, and Z positions. So we should see all of our point clouds move by this error. And what we want to do then is manually modify the connect_transform.launch file to improve calibration. Okay, so let's try to run it with this wrong transform. Come back over here. Okay, and kill this. So here we can run connect2.launch. Okay. Then we're going to do connect_transform.launch. Maybe I'll run it here. Launch. Okay, that's where we're going to run this incorrect transformation. Then we can do the coordinator and then the play file node. So here goes the coordinator. And then we can run that play file node one more time. And immediately you can tell that the point cloud has some important problems. Here our blue point cloud is far away from the forearm and from the upper arm, and then right here this lower limb is also quite separated from the actual arm. So we see that here we have some big changes. So in terms of giving you an example of modifying transformation numbers manually, what we can do is come back here to this window where I had connect transform, and then do a raw set on it and say, okay, well, it seems like I need to move this, I need to fix the Y, so maybe I need to move it in the negative direction a little bit. So I diminish this number, close it again, and then rerun it. This is raw set. Rerun the ROS launch. And suddenly we see that jump of the point cloud. Says that, whoa, that's better. But we still have some difference right here in the z-axis. So let's try to change that. And so you get the idea, right? We change this number, and then we run again. We see, so we're going to get a better transformation, better agreement. And of course, we still have some errors in the x direction, and so we can fix that. The idea here is just for minor adjustments. The technique that we introduced in homework 7 should give you very good results, and this would be useful for very, very minor tweaks. Okay, but it's also an illustration of what a good calibration looks like. Okay, so this is the rest of the instructions for agreement. So from homework 7, we used the Aruco hand-eye calibration package for extrinsic calibration, and once we can achieve this transformation correctly, then our sensory information can be used to plan and execute manipulations. Let's see how we do that in section 15.